Hi, I'm Chuck Gardner from NYSERC, an academic division of the Cyber Innovation Center. Today we're going to walk through a robotics build from the Cyber Literacy curriculum, Lesson 9, Intro to Accelerometers, and Lesson 10, Moon Rover. For our Intro to Accelerometers and Moon Rover build, we essentially need only three parts: the MEMS accelerometer, a pair of 220 resistors, that's a red, brown stripe, an assortment of jumper wires. Of course, the Boe-Bot and the USB cable also play a part. So to start, we're going to work with the accelerometer, and you'll notice in the diagram it's got these two little dots on the top, and we're going to put it in the same orientation on our Boe-Bot. Just make sure that the accelerometer crosses the valley so that these two sides don't touch. Anywhere I can move it down, I can move it up. It doesn't matter. For the purpose of this build, I'll place it right there in the middle. And then we're going to use our 220 resistors to connect pins 1, 2, 3, 4, 5, 6, 2, and 5 over here to pins 6 and 7. And then we'll use the jumper wires to connect grounds and VDDs. And we'll do that for you now. Now that we've got the Boe-Bot built and the accelerometer circuit assembled, we're going to go to the code, and we're going to take a look at some sample code. So now that we've got our Boe-Bot built, we're ready to take a look at the code. First, the accelerometer, this square silver object in the middle of the accelerometer that houses an air bubble with some liquid that's being heated up by the accelerometer board. So what happens is, as the Boe-Bot tilts, that accelerometer notices where the bubble is by changes in temperature and reports those values back through the pins 6 and 7 to the Boe-Bot, which is out of pins 2 and 5 on the accelerometer board. So this information is going to go back through the USB to the Boe-Bot, to the laptop, and we're going to be able to make certain decisions based on those values. So we've got the code ready to go. We're going to run it with a Control-R. And what's important to note now is that the red light is blinking on this dongle. So what that means is we've got a constant two-way flow of information. The accelerometer board is reporting data to the microprocessor, which is sending the information back to the laptop. And on the laptop, we've got a series of 4-digit values. Right now, they're ranging around 2,500. So as the Boe-Bot sits on a level surface, the values that the accelerometer are feeding back is about 2,500. What we should expect is, as we tilt the bot forward, one of those values, either X or Y, is going to change. And in this case, as we tilt forward, the Y value increases. At this point, it's almost 2,900. As I tilt the other way, the Y value decreases. As we tilt to the right, the X value increases, and as we tilt to the left, the X value decreases. That's basically the extent of the Intro to Accelerometers build. What we're going to do in BB10, which is the Moon Rover project, is going to take this information and turn it into awareness for the Boe-Bot to make maneuvering decisions. So we're going to go into a sort of autonomous navigation mode. So if we were to put this bot, say, on a foreign land or a planet somewhere, we wanted it to navigate successfully without rolling over. As the Boe-Bot encounters some kind of angle, some kind of obstacle, it's going to begin to tilt. And we want to make sure that before it gets too far, we tell it to back down and maybe turn away from that obstacle, assuming that there's an obstacle here. As the Boe-Bot tilts to the left, we're going to see a decrease in the X value. So the response from the Boe-Bot would be, if I see a decrease in X, back down, turn to the left, and then navigate forward again. If I see the obstacle on the left, Boe-Bot's going to tilt to the right. The X value is going to increase. In order to stay flat and level, I want to back down, turn to the right to avoid that obstacle, and then maneuver forwards again. So what that program looks like, it's got a series of if-then commands. And I've picked an arbitrary 150 values. So if 2,500 is level, I've assigned 150 to be a danger zone for Y and a danger zone for X. If the bot tilts too far forwards and Y goes beyond 150 from 2,500, which would basically be 2,650, then I have the bot instructed to roll backwards. If it tilts too far to the right, where the X is increasing beyond 150 from 2,500, which is 2,650, then I'm going to want it to back down and turn to the right to avoid that obstacle. If the bot tilts too far to the left, 150 off of 2,500, which would be 2,350, then I want the bot to correct and turn to the left. So if we upload this code, we'll take a look at what the result is. So what happens here, the bot doesn't do anything. It's always good to instruct students to program on one, especially when there's motion happening. because if they were to program this on 2, knowing that the bot was supposed to be rolling, if it was too close to the edge of the desk, we don't want it to fall off. So at this point, it's safe to turn it on to 2, and we notice the bot rolling forwards. As we pitch down, the bot spins backwards, back on level ground. As we begin to tilt to the right, so what the bot's going to do now is going to turn to the right because it knows the obstacle's on the left. And similarly, as I pitch to the left, the bot's going to turn to the left because I know where the obstacle is. So we've got some sample code on the screen. This code also includes your series of forward, back, left, and right subroutines. Just make sure you've got them ready to go, and this program's good to go. And that's the Moon Rover build.